Okay, let's get started. So I'm happy today to have Dr. Govindarasu from Iowa State University. He's a specialist in cybersecurity for the power grid. Been at Iowa State for 20 years, I think that. His PhD was from IIT tonight, and then he came over here. He started working in the power areas, primarily computer engineering, but he started working with power folks about 15 years ago now, a little kind of while after he got to Iowa State University. And so he's been one of the premier people doing cybersecurity for the power grid, and I guess he's going to talk generally about what he's got and perhaps a little bit about his test bed. So that's for all mine. Thanks.
Thank you, Kevin. Really appreciate the opportunity to be here. And I know the current center, Engineering Research Center, is a national facility. It does research, development, and also a lot of outreach activities for with the industry engagement and also high K-12 education and so on. I really applaud the great work that is happening at UT here and also with your collaborators in other universities. And I have known Kevin through IEEE. Students, you all know what is IEEE Power and Energy Society. Through those forums, I have known him for years, and I have always respected the quality of work he and his students have done over the years, and many of the work we have followed, trying to understand how we model cybersecurity. We have followed a lot of his work in the process. So, again, thank you all. So, what I'm going to do today, I'm going to give you sort of high-level overview about this whole area. As you see the title, Cybersecurity for the Power Grid in the face of growing challenge. That means adversaries are becoming more and more sophisticated. The number of attacks that are happening on the grid and other critical infrastructures are increasing in number, not just in the United States, throughout the world, and also in sophistication. They become more advanced over the years. As a researcher and industry and students, we all should be vigilant how we educate ourselves, what kind of technologies we develop, so that we are one step ahead of the adversary, so that we can prevent these attacks happening on the grid or other critical infrastructure. So I am a faculty member in the electrical and computer engineering, similar to what you have here. So the outline of the talk, I'm going to set the context. So what is cyber threat and some of the attacks to kind of bring everyone up to speed. We all read about this is a growing problem in national media, newspapers, and so on. Then I'm going to offer some solutions. Some are related to what you can do in the IT security. As you know, cybersecurity for the grid is basically an interdisciplinary field. So some of the problems can be solved through IT security. There are other problems that require collaboration between cybersecurity and power engineering. So some of the CPS, cyber physical system security, I will provide some example case studies. Then I will talk about cybersecurity test bed. It's a playground where researchers, students can conduct experiments, conduct training, education. You can play with things before you actually commission deploy the product in the field. You want to test them in a lab environment, in a controlled environment. So I'm going to briefly talk about our experience in building test bed, what kind of engagements we have had with the industry and students and so on. So finally, conclusions. So hopefully we'll have some time to answer questions at the end that you may have. So just the modern view about the power grid is no more a physical system. This is a diagram from NIST framework document that was developed in 2012. So the modern grid, you can call it smart grid, is a cyber physical system. Power grid was physical system, lot of sensors, automation, communication happening everywhere, from consumer side all the way to distribution to transmission, generation, everywhere. Smart sensors, smart advanced communication, and various computational analytics. Those are all happening. That's why the cyber element is expanding in number, in size. That's why it is a cyber physical system view. So what you see in this diagram, the traditional generation, transmission, distribution, and customers at the bottom. What do you see on the top? Like the operational control center, or regional control center, market operations, various kind of other decision-making services. Those are all IT or cyber. So when I say cyber, the smart sensors and communication and the associated analytical thing, computation that goes on in servers and cloud and so on. So those are all cyber. The cyber is superimposed on the physical to make the old power grid, so-called power grid, into a smart grid. Okay, so but those are all great things from the economics perspective, from efficiency perspective. What happens if somebody hacks into the cyber layer? Because they are expanding the cyberspace, they are susceptible to attack. If somebody gets in there into an operational environment like a control center or substation, you will see some example. They can basically create a blackout in the grid, or they can damage huge generators or transformer or any equipment by manipulating the settings, control settings, set points and things like that. Or they can oscillate the market behavior by changing the price signals and so on. So cyber is vulnerable to attack, and those vulnerability will result in impacts on the grid operation in so many ways. So the whole idea of cyber physical security is how do we systematically understand those vulnerabilities, how do we develop mechanisms, techniques to detect, mitigate, and keep the grid resilient in the face of all those attacks that are likely to happen. Of course, the grid is designed to withstand natural events to a large extent. If there is a massive event, there will be a regional blackout for sure. But the grid has enough resiliency and capacity to deal with simple events. But when it comes to cyber adversary, they are going to choose when to attack and where to attack, how many components they are going to compromise as part of the overall cyber attack orchestration. So the enemy is hidden. That's why the conventional paradigm that we typically use for fault resiliency, they no longer apply to what is called cyber attack resiliency. So I'm going to touch upon those points. But the point here is a lot of communication, a lot of sensor, a lot of control that forms the cyber, and the cyberspace is expanding. So this is another view about the power grid from the architectural perspective. What you see at the bottom, you have a substation environment. There's a lot of automation, local area network, PLCs, intelligent electronic devices, all those things. It is a substation environment. You see the generator, transformer, and the other kind of things, but there are a lot of cyber inside. They in turn connect to the control center. You can think of like hundreds of substations connected to the control center as part of the regional environment. So those whole thing on the left side, you can think of as the OT, operational network. Okay. On the right side, you have corporate entities. They communicate with the control center for market and other functions. There is an IT, OT interaction, IT network or corporate network talking to the operational network for market and other reliability studies that exist. Many times, engineers sitting in the control center, remotely maintaining the substation equipments. That's what they do. They don't physically go there. So there is a lot of connectivity. It is a legacy infrastructure. This has been developed over a period of 100 years or so. The technology slowly changed. So how do you secure the legacy infrastructure with all kinds of communication technology, all kinds of devices? Some of them may not be capable of using the latest encryption or authentication or any security technology that you can think of. So the key is how do you retrofit security into the legacy grid so that it is resilient against attack. If you are to build a brand new grid, yes, you can keep all those security features in mind to begin with, but you have a grid already operational. You can't dismantle and rebuild things. So the problem becomes not just from the adversary perspective, they are becoming smarter and sophisticated, but also from the legacy nature of the grid, retrofitting security is challenging. So there are two areas in both angles we need to address the challenge. That's what important. Who are some of the attacks? Different type of attacks. Some of you very well know. There are a lot of publications from the Government Accounting Office, GAO. They look at all critical infrastructures. They kind of grade them, how secure they are in terms of various things. Just to motivate those agencies like DOE or other agencies to advance their R&D and deployment and things like that. So in those documents, they identify all critical infrastructure, some of the commonly known attacks. They could be protocol or social engineering intrusion or malware of different kind, or just flood the network with the denial of service attack to slow down the communication, especially in the grid kind of context. It's a kind of real-time system that will have impact. Of course, insider threats. One important thing I want to highlight here, social engineering has become spear phishing. I'm going to use that word later on. Social engineering to just fool the operator or fool the employee, find the weakest link in the whole security chain, that is the human. Humans are operating the system. They tend to make mistakes. That becomes the exploiting point by which the adversary get into the system and have a foothold, then try to do other things. I will illustrate that. So social engineering is the most common form of attack. That's why it is not just technology, it is beyond technology when it comes to cybersecurity. The other one is malware. Malware has been spreading, several malware. Probably you heard about Stuxnet, that was targeted towards uranium enrichment facility in Iran. That was a malware. So malware and social engineering, those are commonly used technique to get into critical infrastructures. So this is just to show the threat landscape. This is a report from DOE and NERC, North American Electric Reliability Corporation, Industry Consortium, DOE Department of Energy. So it simply says what is the likelihood of some cyber attack happening. There are different grades, or simply somebody scanning, all the way to having a cyber warfare, nation state getting involved. They give what is the likelihood, probability of that happening. Similarly, what would be the consequence? Okay, somebody scanning, it is not going to create any major outage, but somebody is having a very focused effort to manipulate the measurement, manipulate the control, that may have high consequences. If you look at the trajectory, probing very likely, but consequences very less. Then system compromise, they go all the way. You go to the rightmost on the top, those red zone, those are having high risk. That means when you multiply the likelihood with the consequence, if it is high, you have a high risk. So the idea here is just to lay out what is the cyber threat landscape. The problem with this chart, probably this was right when it was developed several years ago, 5-6 years ago, but this is no more valid actually in my view. You ask other experts or other people who work in the area, they would say, hey, this is no more. So for example, if you look at nation state engaging in cyber attack, it's less likely. No, that is very likely actually. A lot of things happen because of nation actors. So the point I want to convey here is having this threat landscape understanding about likelihood and consequences is important, but it is continuously changing. As the utility industry or R&D organization, they have to reassess this whole thing as things are moving. Nothing is static, especially when it comes to cybersecurity. It is dynamic. So the other point I already illustrated. So you see a lot of substation connected to control center in the middle through wide area communication network, taking measurement data, going to the control center runs all kinds of computational algorithms as part of the energy management system. Then they basically control your substations to increase the generation, reroute the flows, or open the breakers, whatever that may be. That is a typical SCADA loop. Then on top of that, you have market and utility corporate environment, and the adversary is somewhere sitting in the internet. The internet is connected to the corporate network. So the attack surface keeps expanding as we produce more and more things like Internet of Things, IoT. Okay, everything you have, every gadget is connected to the cloud. You can monitor your thermostat, control your thermostat from your smartphone. That means the attack surface expands. So how do you systematically assess the attack surface and how do you reduce the attack surface? We are not saying that, oh, you should not automate, you should not go for cyber. When you go for it, what kind of security controls you have, what kind of authentication and authorization you have. those things are extremely important, not just adding cyber is good enough. So that is important. So what I'm saying is adversary sitting somewhere in the internet, they can get into the control center by going through the IT network, the corporate network. From their control center, from there they can go and trip all the relays in the substation and create a blackout. So that those things are possible with this state. This is just to bring that point. The cyber attack is growing. This is a 2015 report from Industrial Control System CERT, which is a kind of DHS entity, collect all those attacks or vulnerabilities that have been reported in industrial control system. If you see all the critical infrastructures, in that the year, like 46 different attacks, or at least attacks not to the extent of blackout, but something to be considered as an attack that happened compared to many other things, critical manufacturing being the highest one. When they looked at those energy system incidents, what is the major weakness, where exactly that originated from? You see there spear phishing. Spear phishing means somebody sent you an email with the same nice attachment, entice the user, you go and click the attachment, that is a malware gets downloaded and give backdoor access to the adversary. Or you click a link or do things of that nature using social engineering. Spear phishing happens to be the weakest link so far from that report or any such reports that have been identified. So social engineering, spear phishing, all those things, when we are talking about it, is about human, about education, about training, awareness. Those are extremely important. Then of course there are network scanning, probing, those are technology related, some authorization, access control, those are technology related as well. So just to let me take you to something real that happened. It's not hypothetical. When I started this research 10 years back, when I go to utility, oh, you are just kidding, this is not going to happen. Government recognized it is coming, but it is real. So you see there in Ukraine in 2015 December, just before Christmas, it happened. It was believed that Russian hackers, they basically waged that war. It was a coordinated, very sophisticated attack. Coordinated means multiple events were orchestrated as part of the attack. So 3 distribution companies involving 29 substations were targeted. Those 29 substations were removed electrically from the grid by turning off or opening the breakers. That's what happened. So they used the attack path was spear phishing. I will show you. Then they, I will show you the exact details that happened. That is the regional map. One region fully blacked out, 2 other regions partially blacked out. So if you try to understand the anatomy of what actually happened, we in fact have this implementation in our test bed, but this illustrates there is a corporate network somewhere. Companies have corporate network. There is a SCADA, there is a substation underneath, within that protection, and all those devices are all there. So if you look at the steps, some are in the IT world as part of this attack, that is the entry point. Some are going to be in the OT world. From IT, you hop onto the OT, operational network. When I say you control the grid, that is the operational network. When you use your computer for regular browsing and other kind of office function, that's the IT network. Then post OT also they did something. If you see there on the thing, the very first event was phishing email that was sent to somebody in the corporate network. Okay, it was sent. That the individual basically happened to click that link or open that file. That downloaded a malware. It escalated the privilege. So then it was monitoring. It happened that the engineer sitting in the corporate network connecting to the control center through VPN, virtual private network, to do various things. So they basically monitored over a period of time what is the VPN credential, user ID, password, those VPN credentials were harvested. Then install some malware there to observe other behavior, how they are actually controlling the control center to operating the grid itself. Okay, this is the operation they are doing. Then they basically using that stolen VPN credential, log into the control center from somewhere, because you need, like you want to log into your bank, you know what is the user ID, password, and the VPN. Same way they log into the control center through remote human machine interface. That means they were able to get this HMI in front of their own computer, then trip the breaker. 1, 2, 3, 4, like that, they trip the breaker. The operator who was in the shift, he was about to leave. In front of his eyes, he was seeing that the breakers were being tripped off. What is going on? He was trying to stop the mouse and keyboard, all those, disable the keyboard and mouse so that the operator cannot do anything. Then subsequently, they also, the uninterruptible power supply UPS, which powers this thing, that was brought down. The telephone network that was brought down. Those ideas are to delay the restoration process. And in the process, all those PLCs in the field, they were uploaded with bad firmware. That means they got corrupted. If the engineers want to reconnect those substation back to the control center, they were not responding. So essentially, physically, they have to go and replace each one of those PLCs for them to be communicating with the control center. So some are the targeting to the attack itself to create that regional blackout. Some are to delay the restoration process, to make the restoration process difficult, for damage the PLCs in the field and also UPS and telephone data so that the customers don't call. This is what happened. Believe it or not, 225,000 customers were without power for about 9 hours. It's a real incident that happened. So, I mean, the same thing, I don't want to go there. There was another incident in 2016, happened exactly 1 year after. It was not regional, it was in the city of Kiev. A similar incident happened, but it was quickly restored. It was but more advanced in terms of attack. Of course, the defenders also tried to put in some safeguards and so on. So let me go to the next step. So we kind of understand cybersecurity is a growing challenge, or the threat is increasing and so on. Real incidents have happened. So what can we do from a security perspective? So before going into security itself, from a power system point of view, people say, oh, cyber physical system. Oh, cyber is there, physical is there. Oh, there are a lot of things in between. That's what I want to illustrate. So the attacks, whatever the attacks could be now in the middle, or spear phishing, or denial of service, those are all happening from the attack. It is not just to changing things randomly, but it has to go through various steps. So it has to compromise some cyber elements, maybe HMI or IEDs or relays or PMUs, whatever are network routers that are there as part of the SCADA network. The cyber elements have to have some vulnerability for them to be exploited. Otherwise, they can't be exploited. So once somebody gets into the control center, okay, what are they supposed to do? Okay, you say give it to IT person, that person knows how to get into the control center, but they should know how the grid operates so that, oh, I need to go and open this breaker, or critical lines can be opened so that it has the maximum impact. So that requires the knowledge about control, power engineering basically. That's where you have different kind of applications that is running as part of your control center, energy management system or distribution management system, if it is a distribution control center, related to generation, transmission, or distribution. They have to systematically manipulate those, create those control actions through the exploitation of cyber layer. That is what will create blackout. That is what will create the stability problem related to frequency, voltage, or whatever, or economic impact through equipment damage and so on. So it's not just magically from attack to physical, but there is the intermediate steps. That is where the interdisciplinary knowledge is coming to picture. It's not like the IT people alone create a blackout. They had expertise in the power engineering, how it operates, and that's inherently interdisciplinary from not only attacker perspective, from a defender perspective. So some of the solutions, one is a defense in depth, is a very famous concept. Okay, you put multiple layers of security, layer 1, layer 2, if somebody penetrates layer 1, then layer 2 is there, layer 3 is there. Each layer is sophisticated, incrementally advanced. That's the way it should be. It cannot be inferior. So for example, from a power grid context, so you see the conventional firewalls are the outer layer firewalls, intrusion detection system, whether it is a power grid SCADA environment or your conventional IT like a university or enterprise, we have firewall, we have ideas that forms infrastructure. Then the inner layer, next layer, you have information security. Do you have proper encryption? Do you have proper authentication? Do you have password management and things like that? They fall into the information security layer. Those are all there in all those environment. We have like a bank or university and hospital. All those two layers are there. But equally important, the innermost layer, the application specific, domain specific security, understanding the underlying physics of the environment. In this case, the grid. Okay, grid operates a certain way. Can we codify some anomaly detection? Can we develop some control algorithm that leverages those kind of properties so that when something bad comes, we can reject those. The idea there is some attacks we will see, like the Ukrainian attack. Oh, the operator was sending a command. That's what the substation thought if they opened the breakers. If there is a way to detect, hey, within short span of few minutes, this many breakers are getting opened. There is something is wrong happening. Normal operator would not do such a thing. If you have an intelligent anomaly detection at the substation, which understand the behavioral property of the operator, it would have rejected. It may have allowed one or two trip in the beginning, then it would have rejected the subsequent trip. That would have prevented the blackout itself. So there are various techniques that can be developed, whether for control, attack resilient control, or anomaly detection, or other kind of thing that can leverage or making each of those energy management system applications secure, leveraging those underlying physics or physical system property. That is where the application level security, I call it model-based anomaly detection, mitigation, and all those things fall in. That is, so you have a difference in depth. If you think about like a vendor, you have Microsoft product in the grid environment, you have Cisco routers and other things in the grid environment. They have to be secure. On top of that, we have ABB or GE or Siemens, those companies, SCADA and EMS or DMS application. They need to have security inbuilt, which are more specific to the application. They can catch bad data if the other layers did not. Right, so that's where the difference in depth comes in. And a lot of our research, people who try to work in the interdisciplinary, we focus on application-related security, not just conventional IT security. Those products anyway, there we will try to leverage them. So you have a difference in depth is one important architectural concept to secure the grid or any critical infrastructure. But the key is when you try to add more and more layers of security, it has to enhance the security. You can't just have a false sense of security. I have multiple layers. If they are weak, then it's not good. And the other thing is, additional layers will burden the system in terms of latency and other kind of overheads. Is it consistent with, or is it acceptable within the SCADA and other applications that we are running? If you have more band-aid, then it is not going to solve. So it has to be properly architected. The other concept is, like I was talking about, there's IT network, corporate network, OT network. Yeah, they need to talk to each other for sharing load forecast and other information for market application. That's great. But if you just let them go, like the example I showed, things would have gone wrong, right? The Ukrainian attack. There is a concept called demilitarized zone. That means you want to share, at the same time you want to keep some area buffer zone. Whatever you want to share, put it into the demilitarized zone. The other one can read it from there. The other one can put it there. The left side can read it. So, like for example, between warring nations, like right now the Winter Olympics is happening between North Korea and South Korea. There is an intermediate buffer zone called demilitarized zone. That's where people know that the peace is always maintained. People go and meet each other. That kind of concept. So, the similar equivalent to the normal war zone kind of situation. We have demilitarized zone concept using firewalls and other things. You have two firewalls, they are properly configured, only one-way traffic, this way or that way. Then you have demilitarized zone. So segmentation and demilitarized zone is important concept in the other thing, in addition to defense in that. So let me just quickly move through. Just to summarize what I said, defense in depth, information security, infrastructure security, and system, application, and control system security. Of course, physical security is important as well. The other important thing is this is the DOE kind of when they fund project and so on, they try to see where this project makes contribution. So what you see on the rightmost is the generation all the way transmission, substation, feeder, automation, home, end-to-end delivery of the grid. Every point, there is cyber, the cyber is expanding. So looking at security in an end-to-end sense also important, not just say, hey, I secure my transmission grid, but distribution grid is open to attacks. Then doesn't help much, right? The impact may be smaller in scale compared to affecting a transmission grid, but the way it happened in Ukraine, it was not targeted in the transmission grid, only the distribution grid was targeted, but multiple distribution companies were targeted. Then you can create a regional blackout by compromising enough number of them. So you need to have security in multiple layers, but it may not be at the same level of depth, but security is across board. This is, if you are interested, there's a paper which talks about this concept. This is essentially to show you want to deter the attack. If you start with it, attack is their deterrence. Okay, deterrence means, okay, let's not attack each other. This kind of pacts exist between nations through United Nations and other forms. But we are dealing with cyber security or cyber attack. Many times the attackers, they are hackers, and the people know they want to make money, or other activists and so on. The rules of engagement doesn't work. Any internationally agreed laws don't work. So you can deter some people who obeys international laws, like some states, many states probably. But that will deter some cases, not all. So you need to go beyond deterrence. This deterrence also involves a lot of governmental related things, not necessarily technical. Prevention, trying to prevent the attacks. That's where all kinds of advanced technologies, encryption, firewalls, intrusion detection, risk assessment. You want to assess the risk through threat landscape, and systematically you upgrade your infrastructure with the security technologies and so on. That is a prevention technology is important. Not every attack is preventable. There are zero-day exploits. That means the vulnerability is not known. Only the hacker knows there is a vulnerability. Before the patch becomes available, they penetrate into the system. So you need to prevent as much as possible. If not, you should be able to have technology to detect, okay, online anomaly detection or other kinds of techniques. Hey, there is something goes wrong. Detection capability is important. Once you detect the things, just flashing alarm is not good enough. You need to have capability to mitigate those attacks. How do you overcome that situation? Of course, the resilience is a much bigger concept to keep the grid stable and operational with minimal impact with things like, we may have islanding or load shedding or doing other kinds of things, part of the resilience strategy. Those are all important. Then, of course, attribution. Attribution is if you're able to identify where the attack came from, you can make them accountable, or if you still make the world know that I can catch if somebody attacks me, then people will think twice. Suppose if you have your home now has a AAA security system, then the burglar will think twice before coming into your home. So, but the challenge is having attribution or forensic capability in the grid, internet, everywhere. It is very challenging because they don't have state information. Always know where the attack come from, nobody knows, because the attacker use various kind of indirect methods to hide behind the actual source of attack that comes from. So attack attribution is challenging, but attribution could help deterring many attackers because they will be caught and they will be held responsible. So the key here is deterrence. We need technology, policies, maybe some technologies, prevention technologies, detection, mitigation, resilience, and attribution. Everywhere there are research challenges, research opportunities, not for internet, not for critical infrastructure. Everywhere this is equally applicable. I kind of codified some of the science of security, what in theory could be a tool, stochastic optimization, machine learning, those are kind of mathematical tool could be utilized. Some of the enabling technology like synchro phases, a lot of work going on here in the current center related to power synchro phaser, wide area monitoring, those kind of technologies. They could be leveraged. Cloud computing, Internet of Things and things like that, can they be leveraged? Software-defined networks, some of you may know. Some of the things are happening in the technology field, some of the science that is happening, whether they all can be utilized to solve these problems in a much more practical and using sound mathematical and analytical foundation. And of course, you need data sets and test beds and all those things to validate before actually going to the field. Just coming back to the left side, what is the goal long term? The current grid is fault resilient actually, in the sense if there is a fault happen, it is able to recover it unless now there is a massive snowstorm that wiped out a region. US grid is fault resilient, N-1 resilient they call it, but it can tolerate more than one fault if they are in different locations and so on. How do you transform the fault resilient grid of today into an attack resilient grid of the future? Because in fault resilient, you can weather forecasts and other things where you can expect where the fault is going to come, also condition monitoring of equipments and so on. But when it comes to fault to attack, attack is who is your adversary, when they are going to attack, where they are going to attack. It's very hard to even predict. So just using the conventional fault resilient methods or techniques, they are grossly inadequate to deal with attack resiliency. So there is a fundamental paradigm shift is needed when you think about attack resiliency. That is important. When as I said, it's not just a technology problem alone. Process is related to the government and industries. They need to have a systematic process to validate and assess and verify all those things. The compliance in place, critical infrastructure protection compliance, those are regulatory things. Of course, the people, training, education, like I said, spear phishing in the Ukrainian attack, it happened, and many other Stuxnet possibly happened through that means. So technology, process, people, and regulation, all are equally important. We as a university, we play a role in technology and developing human resource. Those are the two places. Industry and government, they have their role to play, including national lab, like Oak Ridge National Lab and so on. They have a role to play in technology and processes and educating workforce as well. So some of the things, these are important. Let me, just so far I kind of gave you overall big picture, defense in depth, segmentation, demilitarized zone, those kind of concept, plus that security life cycle view from beginning to all the way end. How these things we need to look at and what are things we can do. Just to give you some sample ideas. So at the control center, substation, and the SCADA network, various things can be done. I kind of alluded to anomaly detection, which is domain specific than just IT-based anomaly detection. Beyond IT anomaly detection, that is one thing. It could be at the substation, it could be at the control center. The other one is the moving target defense. I heard somewhat similar research is happening at Oak Ridge National Lab as well. So moving target defense, basically the idea is to confuse the adversary so that they don't have an idea what's going on. But whoever is involved in part of this operation, they know what is being confused. So for example, let me introduce, suppose you have a substation, somewhere substation is at the bottom, there is a control center on the top. They are going through the wide area communication. What you see here is there is a wide area communication in the middle, one substation on the bottom left, one on the bottom right, substation B, on the top the control center. So substation to control center, let's say adversary is trying to inject trip or other command, bad command. So let us say substation and control center, they keep changing their IP address. The address, IP address for routing and all they use, change the address so that the adversary doesn't know which target to target. You keep changing, but we know the substation control center, they know what address they are changing. They have a kind of peer-to-peer protocol through which they randomize the address space so the adversary doesn't know what is the current IP address. By the time the adversary knows, hey, I grab a packet, oh, this is the IP address they are using, I'm going to set an attack, by the time they would have changed to something else. The adversary is always lagging behind, or the operator or the system will be one step ahead of the adversary. That is the way you win the game, especially in the cybersecurity game. Make it extremely hard for the adversary to break, or you be ahead of the adversary. That is the technique. Moving target. So introduce controlled uncertainty. Control, that is very important in the system without adverse effect in the system operation. Let's say when you are changing the address, if the substation is not able to communicate with the control center, then it's a problem. You should be able to communicate, but you should prevent adversary able to inject anything. So confuse the adversary, randomize the network connectivity, IP hopping is the common technique we use. There are other
forms of technique. For example, many of you are in power engineering. When you do state estimation, you get measurements, status and analog measurements from the field. You take more sample. You take more measurements than needed for state estimation. Then you randomly select only a subset of measurements as part of your state estimation. The adversary doesn't know which measurements you are going to use. Sometimes you use this, sometimes you use something else. But the key is you need to still maintain the observability property whenever you take that subset. So the redundancy, having redundancy, within the redundancy you do randomization is a common technique. So you can have a moving target defense at the application level, like a state estimation I mentioned, or at the network level, or at even at the physical level. People use different kind of techniques to keep one step ahead with the adversary. It is essentially a prevention technique, like measurement randomization is possible. So I kind of introduce some basic concept. Let me take maybe 5-10 minutes to introduce, as I said, 3 layers as part of the defense in depth I talked about. Infrastructure security, IT infrastructure security, information security, then the application security, where it has the cyber physical CPS, cyber physical security. So one way to look at the power system as a cyber physical system, you have a physical system, a lot of measurements are there. The measurements go through the wide area network. The cyber system is the various controllers that take decision. The control action comes back to the physical system, the actuation is done. Continuously this loop happens. There are hundreds of loops in the power system doing various control actions. Some are within the substation, some are substation to control center, some are at the regional control center. It's a complex infrastructure with different time scales of feedback control loop. And some loops are automatic. That means there is no human in the loop. Some are supervisory. When the control center operator is sitting, they look at various things, then they push the button. This is the control action based on some analytics they have done. So supervisory are there. Also automated control loops are there. In abstract form, this is what the sensing measurement, they could be subject to attack. There is a control signal that could be under attack on the network. If it is everything within your own building, nobody is going to come here, then attack is less likely. We are talking about wide area. So the sensor measurements, so you can see there are different types of attacks that are possible. So the idea is how do we, so one could be data integrity attack, go and change the measurements values or change the control signal itself. Okay, open the breaker instead of say close the breaker. Shift generation, shift up, ramp down, do all kinds of things. Those are changing the values, that is data integrity attack. Denial of service means, okay, the channel is encrypted between substation and control center, nobody can tamper with it. Still, at least I can go on to inject a denial of service attack to flood the network so that the substation or physical system measurements never reach the control center or coming back the control signal. So DOS attack is possible, or I can just, I don't know what is the signal, but I hold the old packet and replay it. Replay attacks, that means if the channel is encrypted, I can do replay attack. Those are all possible. So what I'm saying is, just going by the traditional IT security and information security, what I articulated before, encrypted channel and the firewall, all those things, still one can create a timing attack, replay attack, denial of service attack to create impact on the grid. So we need to go beyond the conventional IT and information security. That's the point. So same diagram. So you have sensors and actuators and the various things. The control could be remote or local. So there are various applications that fall into this control taxonomy. In fact, I was referring about a paper by Kevin and his co-authors. We followed similar line of paper, the control taxonomy kind of title I forgot. We kind of use that paper as the basis to understand what are the different control loops are there, voltage, frequency, and the small signal stability related, and kind of categorize them from a cybersecurity perspective. So you see generation related like AGC and governor control. Governor control is a local phenomenon. AGC is a wide area control, transmission, state estimation, and other kind of things. Similarly, at the distribution side, so various control loops are there. They have different time scales of operation. They have different types of sensor, communication networks involved, and control elements involved. Whatever I showed you before, they are subject to this kind of attack on the sensing side or control side. So systematically understanding each one of those control loops and strengthening those applications in terms of cyber security. So how do you transform the simple state estimation into attack resilient state estimation? How do you transform AGC into attack resilient AGC? So this means these applications have some knowledge inbuilt to withstand cyber attack. They will be part of the energy management system, EMS, coming from GE or Siemens or whatever company it is. So that means you have the third layer also secure. That makes the grid a lot more secure than just relying on the IT security. That's the essence of attack. So let me take, let's say, a few minutes to illustrate one example about that concept. So some of you may know, I mean, you all know about protection system, but there is a wide area protection, WAMPAC, we call it wide area monitoring, protection and control, WAP. That means you have some kind of coordination among protective elements like relays, they coordinate among themselves. The moment you say coordination, means there's a communication involved. Coordinate to clear a fault, to sort of do various things to keep the system stable within the whatever is possible. The corrective actions, changes in load, they can do it. They can do load shedding to keep the grid stable and reliable based on some fault condition if it happens. Or change in the generation, they can generation reject or shift and those things. Or change in the topology. I mean, the readout flows and things like that, those are possible. Typically, substations have relays. Those relays are but basically one example is the remedial action scheme. It's kind of a special protection scheme wherein multiple relays they coordinate to protect a critical region where whenever the fault happens, those faults are properly taken care. You can go to codify these RAS related rules. Okay, such and such thing happens, you do generation rejection or you do load shedding or you reroute the flow. They go clearly define ahead of time based on all possible contingencies. They can think of. So there is a RAS controller which gets the information from this substation. Keep in mind, these are not going to the control center in any place. By the time it goes to the control center and the decision comes back, it is too late. This is a much more faster time scale, like 100 millisecond or even less than 100 millisecond. The fault has to be cleared. So it is a lot more localized in a peer-to-peer way as opposed to going to a control center application. So one example, many of you are power engineering students, you might appreciate. Here I have 8 bus or 9 bus system. There are 3 generators, one at the bottom, one on the left, the right, one on the right, G3. So there are several buses that are there. So RAS is not there everywhere. They are going to implement in critical part of the grid. For example, the RAS scheme is implemented in Southern California Edison, SCE in California. So what they do is, for example, there is a bus B7 and B5. There is a line in between. The relay R1 is there. Then relay R2 is there on the between bus 7 and 8, right there. It monitors that particular line. So then there is a RAS controller. It is somewhere sitting. Let's assume. So what happens? Let's say the relay line 1, let's say B7 and B5. That line is off. That means that relay will sense, R1 will sense, oh, that line is outage. What it will do is that it will notify to the RAS controller. What the RAS controller will say, hey, okay, one of those lines, the output of G2 is basically bifurcated between those 2 buses at the bus B7, between those 2 lines. One of the line is down, then what it will do? It will basically, the RAS controller will tell the G2 ramp down because there was 2 outlets. One was going straight to bus B8, another was coming to B5. So the line between B7 and 5 is off, or it is outage. So basically, ramp down. That is a normal operation. So change the generation, ramp down. Of course, the other generator G1 and G3 they may pick up other ramp up to satisfy the load to keep the grid still normal and stable without load shedding. Sometimes they may have to shed some load, but that's a normal operation. Let me illustrate a cyber attack scenario. Somebody knows this such a scheme is in place. One can orchestrate a coordinated attack. Coordinated attack, for example, you have that R1. I can go and trip that relay, like some techniques. The relay is tripped. the RAS controller will send a command to the generator 2 to ramp down. I'm going to do DOS, the RAS controller, put a denial of service, so that whatever command it is sending never reaches there. The generator T is G2, it continues to send its normal output. So what will happen, the line, the top line you see between bus 7 and 8, that will exceed its capacity because every output of generator 2 is going through the flow. So the relay 2, what you see, it will sense overload, thermal overload or line violation, it will trip by itself. So basically the adversary caused R1 to trip by an attack, then DOS the controller, causing the system to create a cascading event. That means R2 tripping by itself is a cascading event. So this is a simple illustration. Because of that, what happened? G2, B2, B7, that bus, the whole thing is isolated from the rest of the grid. That will have, of course, other implication in terms of serving the load, or it may, depending upon how big the generator load loss is. If you have a complex network like this, you systematically go and create this kind of attack, then it can kind of isolate, create a network blackout and partition. These are some results to show that how much DOS attack you need to do it on real controllers or real routers. We have done a lot of experiments. If it is a relay is a simple device. If you flood it quickly with 1 Mbps, 2 Mbps is good enough, it cannot respond. On the other hand, if you have big routers, you need to send it several volumes. So typically what you see on the typical latency is like 100 millisecond, 2 milliseconds, depending upon what is the volume of DOS attack. And in this case, the protection fails if it exceeds 100 milliseconds. That means the protection function fails. So any attack that injects large volume of packets, causing the latency goes beyond 100 milliseconds, that is a failure. The protection system fails. Protection system fails means it will create a subsequent secondary event and the cascading outage. So we are working on this kind of template, and we have developed some anomaly detection. This is just to show the power flow and the generator output. For example, the green line, what you see, after the second tripping happened, its generation is 0. That means it is completely isolated from the grid. So it's very detailed information. There are some publication about it. So the second quick example I want to cover here is AGC. As I mentioned, it's a wide area control algorithm. Its goal is to, or its responsibilities within the balancing authority to keep the frequency at 60 Hertz. When the supply and demand, they match, the frequency will be kept at 60 Hertz. If the supply is in the excess, the frequency will go above 60 Hertz. You can see the scale, it will tilt towards the right if supply is more. On the other hand, if the demand is more, the load is lot, then you basically, the frequency will go down, then you need to increase the generation. So the idea of AGC is to ramp up or ramp down the generation so that the frequency is balanced at 60 Hertz. This is done every 4 seconds. It is a completely automated loop. It gets the measurements from the field. I mean, this is just to show in the US grid. Little bubbles, what you see, those are called balancing authorities. Those balancing authorities, that is where this AGC algorithm is run. Many times in the control center, sometimes in the regional control center, to balance the region or the whole utility environment frequency at 60 Hertz. As you know, the grid has to operate with a tight frequency margin. If it exceeds certain band, it will create secondary effects, and the power quality and other issues will come into the picture. So strictly regulated. If there is a violation, there is a huge penalty. The FERC penalty will apply. So every utility will keep the frequency within the acceptable band. There are different bands are there depending upon how much deviation you have, the penalty will be different. So this diagram is a little bit misleading. There are about 56 balancing authorities in the United States. So then there is an interaction between balancing authorities, intertie. I buy some power, sell power. It's not just within your own domain. Maintain power exchange at scheduled value between ties. That is also taken care. Sometimes when we want to increase the generation, do you want to increase your own generation, or do you want to buy it from somebody else, which is most economic? That is also taken care by the AGC algorithm. It is an automated loop. Every 4 seconds That's what it is done. So what is the attack? Cyber attack. Again, this is the application level security, control center application. So the tie line sensor flow, look at the flow chart there. Tie line flow sensor that is coming from how much interchange with the neighboring utilities, how much value it is. What is the frequency sensor from substation? You can get in the frequency measurement. Those two are fed to the control center as part of the AGC algorithm. It computes ACE, area control error. If the area control error equal to 0, that means the supply and demand they match, don't do anything. No need to increase the generation or decrease the generation. If ACE is positive, depending upon if we put the equation positive or negative, so the equation ACE is basically what is the deviation, scheduled flow with the adjacent unit versus actual flow. Similarly, current frequency relative to the 60 Hertz. So basically, you will decide if it is high or low. Depending upon that, it will issue a command to the generator ramp up or ramp down. That is a function to balance the frequency. What can happen is the adversary can go and systematically manipulate the tie line flow and the frequency measurement to cause the AGC algorithm unnecessarily to ramp up or unnecessarily to ramp down, causing unnecessary frequency oscillation. It's very much possible. So these are some plots to show the dashed line. You can see the dashed line keeping the 60 Hertz without any attack, whereas different type of attacks can cause the frequency to go up or down depending upon how it is done. So you can develop mitigation algorithm. The mitigation algorithm typically comes from how do you leverage some load forecast. Okay, you need to estimate what is the current load based on which you can supply the generation. So load forecast, the inertia, for example, you can digitally go and change the value, generate up, down, and like this. The generators have certain inertia. It will take some time to ramp up. You can utilize all those information as part of your model or anomaly detection. That's what we have developed. So what you see is the conventional measurements based on which the ACE value is computed. Then you go through that ACE measurement calculation through some sort of anomaly detection. The middle block is anomaly detection. That is based on the load forecast and some other parameters of the system to see whether it is acceptable, whatever computed value, do a sanity check.